So last time we talked about generalization, and we talked about a sufficient condition for showing that a learning algorithm generalizes. And the sufficient condition was uniform stability. And the statement for uniform stability is as follows. So if you have a training set S, let's say, you have a training set S, you have some point Z, which is a pair of input and output points, and you have some point Z prime. F sub S is the function that's learned by the algorithm on the training set S. And F sub S I Z is the function that's learned on the training set S, where you replace the ith point by the point Z. So uniform stability says that when you do that, when you replace the ith point, the loss doesn't change by very much. So we said that it's bounded by some constant beta. And we said that if beta depends on n, which is the size of the training set, and if beta is decreasing like 1 over n or faster, then we get generalization. Of the learning algorithm. So this is what we showed last time. Now today, what we're going to show then is that Tikhonov regularization actually satisfies this condition. So there is a beta that you can write down for Tikhonov that will bound its stability under perturbation of the training set. And once you've shown that, then you've shown that Tikhonov generalizes. So let's see here. All right. So Tikhonov regularization is as follows. So in Tikhonov regularization, you're minimizing the sum of the empirical risk, the empirical loss on the training set. Oops. And a regularization term, which is the norm in the Hilbert space H, the norm squared of the function. And the notation that we're going to use here is F sub S of lambda. Lambda is the regularization parameter. So in order to show that it's beta stable, then we need to show this. So this is uniform stability. Okay. So this is our goal today, is to show this for that. Yeah.
Are you taking the soup over those three things? I think yesterday you had it for all S and Z, then you just did a soup over Z prime.
Yeah. I think those are equivalent.
Okay.
If it's true for all.
Oh, I see.
Yeah. Okay. So we're going to need two assumptions to do this that we didn't use last time. So the two assumptions are first, we're going to say that the loss function is Lipschitz. and it's Lipschitz with respect to the function argument. And what Lipschitz means, Lipschitz is basically saying that, I'll just write it down, but the Lipschitz condition is like saying that it has a bounded derivative, except that the derivative need not exist. So it's saying that if I vary f by a certain amount, then I can bound the amount by which the loss varies. Okay, and we're using the infinity norm on the right-hand side here. And L is the Lipschitz constant. So we have two functions, f1 and f2, and we can bound the difference in the loss on between f1 and f2 by L times the infinity norm of their distance in the Hilbert space. So infinity norm, by the way, is just the supremum of their pointwise distances. Okay. So this is like saying that it has a bounded derivative. So is this reasonable? For example, the hinge loss, if you remember, we write it down like this. So the hinge loss does have the L Lipschitz property. With L equal to 1. And let's see here. And maybe the most intuitive way to see that is if you plot, probably they showed this plot where you put y of x is the label times your prediction. So if you put y of x on the x-axis and then you put the loss on the y-axis, then you have something like this. So we don't penalize, there's zero loss when it's on the correct side, and then there's positive loss when you make an incorrect prediction. Okay. Now, you can, just by looking at the derivative, if you have a bound on the derivatives, then that, by definition, will satisfy, it will be a Lipschitz constant. So here we have a bound on the derivative, which is 1. I hope that's clear. Yeah. So then, if we look at the square loss, then it won't have that property. Oops. It won't have that property if your domain is unbounded. And again, it's pretty easy to see that geometrically, so there's no bound on the derivative of this. Okay. And similarly, the 0-1 loss which is a step function also has no bound on the derivative because of this discontinuity here. So you can take two functions that are arbitrarily close in infinity norm, and their losses will differ by 1, no matter how close they are in infinity norm. I hope that makes sense. All right. So the 0, 1 loss, square loss, well, the square loss satisfies the Lipschitz property if you have a bounded domain. 0, 1 loss does not, and the hinge loss does satisfy Lipschitz. Okay. So the second assumption that we have to make is we're going to say that, so we said F is in a Hilbert space. We're going to say that H is an RKHS that has a reproducing kernel K, and K is bounded. And by that we mean that it's bounded on the diagonal. So there's some, so we're going to say kappa, which is going to look like K when I write it. There's some kappa that's finite, so kappa squared bounds the diagonal of the kernel. Okay, so these are the two assumptions that we make. So as to whether that's a reasonable assumption, the Gaussian kernel certainly satisfies this because it's equal to 1 along the diagonal. The linear kernel doesn't if you have an unbounded domain. So linear kernel is given by this. Oops. So the linear kernel is unbounded unless you have a bounded domain. Okay. All right. So now to show that Tikhonov is stable, I'm going to basically start from the end of the proof. And we're going to break it down into two statements that will suffice when you combine them to show that Tikhonov is stable. So the first statement, I'm going to write it over here. So the first statement is really just relating the subnorm of these functions to their their distance in the RKHS. So we're going to use this boundedness of the kernel to show that this is true, that you can bound the infinity norm by the RKHS norm. Okay, and then the hard part is going to be showing that you can bound the RKHS norm of the difference between the minimizer of Tikhonov on S and the minimizer on the perturbed training set with respect to their infinity norm. Okay, and that's going to be kind of the meat of the proof. So supposing that we had these two things, then we can show, we can combine them to show this. If we have these two things, then we can bound the RKHS norm which is here. Okay, so I'm going to first just apply this second fact. Okay, we just rewrite using the second fact. And then we apply the first fact to this thing on the right-hand side. To get a bound on the square of the RKHS norm in terms of the RKHS norm, and then you bring down this norm to the left-hand side, and what you get is this. So here we have a bound on the RKHS norm of the difference between the functions on the regular and the perturbed training set. In terms of the Lipschitz constant, the boundedness of the kernel constant, the lambda, and n. All right. So once you have that, then we'll show that Tikhonov is stable by doing this. So to show stability, we're bounding this difference in the losses. And first, we'll just apply the Lipschitz condition. And then we'll apply that first fact. So this is fact 1. And then we'll apply this fact that we proved here by combining 1 and 2. And this will give us the beta stability constant. And this is it. This is, let's call it, this is beta n. And again, we showed that it suffices for beta n to be of the order of 1 over n in order for Tikhonov to generalize, and that's true in this case. Okay, so that's the end of the proof. And so now I'm going to show first this lemma, and then kind of the body is going to be showing the fact number 2 there. Okay, so number 1 is by far the easier one. So we're trying to bound the infinity norms in terms of the RKHS norm. So we suppose that we have some f in the RKHS that and h satisfies the boundedness. then the statement is that the infinity norm is bounded by kappa times the RKHS norm. And this basically takes 3 steps. So you start by just rewriting the infinity norm. Using the fact that this is an RKHS, so you have a reproducing kernel. So you can write evaluation as an inner product with another function. Oops. So this is the reproducing property of the RKHS. And then once we have this inner product, we can apply the Cauchy-Schwarz inequality to bound it. Oops. By the product of the norms of f and the case of x. And so this, the case of x, you can write that norm in terms of the inner product again. And this is just equal to the diagonal element of, sorry, the square root of the diagonal element of the kernel. And we assumed that this is bounded, so we'll say that this is less than or equal to okay.
In that first line, we have f of infinity. Why is that less or equal? Shouldn't that be equal then? The first part of the first line?
Right here?
Yeah.
It is an equal. Oh, it's equal, yeah. So this is just the definition.
Yeah.
Yep. Okay. So that's number 1, and then number 2 is the hard part. And so first, we're going to use a tool called the Bregman Divergence. And I'm going to explain that. Okay. So, all right. So Bregman Divergence it's a generalization. It's like a distance, but it's a generalization of a distance to an arbitrary convex indifferentiable function on H. So we say that f is a functional on H, mapping H into R, and we say that it's convex and differentiable. And what that means is, let's see, so convex, when you have some mapping, we'll just say it's from R into R. So this would be f of x, and this would be x. Then the function is convex if its epigraph, which is the set of points that lie above on or above the graph of the function, if that set is convex. And this definition holds when this is Rn is, this can be any Hilbert space. Yeah. Okay. And the definition of differentiable that we're using here is essentially, it's the existence of a directional derivative in the RKHS. So we're assuming that this limit exists. So h is some function h is another element, is a direction in the Hilbert space. T is just a scalar, and so as the amount that you move along that direction h decreases to 0, then this limit exists, and this is what we'll define to be the directional derivative. In the direction of h. So that's what we mean by convex and differentiable. So the Bregman divergence is defined like this. You have two functions in h, f2 and f1, and then sorry if that's kind of squeezed. So that's f1 over there. So we have the directional derivative at f1 in the direction of f2 minus f1, and then the difference of the functional evaluated at f2 minus functional evaluated at f1. So this is the definition of the Bregman divergence. And the way to understand it, there's really two ways to look at that that we'll describe. So one of these is to note that this directional derivative gives you a linear approximation to the function f at f1 rather. Sorry. Okay. And you can think of this just like a first order Taylor expansion. So if you're evaluating the functional on f1 plus h, then you might say it's equal up to the first order to f evaluated f1 plus this directional derivative times h. Okay. So this is a linear approximation, and what that means then is that the Bregman divergence would be the difference between the functional and its linear approximation at f1. So the functional evaluated at f2 and its linear approximation at f1. if that makes any sense. And then the second way to look at it is that you're generalizing a distance function. And so you can think of it as being, say, like the generalization of the L2 norm. And the way to see that is this. So let's let the functional be the L2 norm squared. Then just writing it out. Oops. And this is going to be a fact that we'll use later on in the proof also. So this is just writing out the definition of the Bregman divergence. We have the gradient with respect to v of the squared L2 norm, which is just going to be a vector in the direction of v. And then rewriting this, we get okay. So L2, sorry, the squared, this could be L2, this could be the Hilbert space norm. The square norm is a Bregman divergence. Okay, so everything that we're going to show about Bregman divergences is going to apply to that. But the Bregman divergence is, of course, more general because f doesn't have to be this distance. It doesn't have to be a distance at all. So there's a couple of key properties that we're going to use for the Bregman divergence. So the first one is that it's non-negative. The second one is that if f1 is a minimizer, let's see, if f1 is a minimizer of the functional f, then man, what am I doing? Then the last term disappears. And you just get the difference between the functional value at f2 and at f1. Okay? So this is going to be a property that we'll use. And the way to see this is that if f1 is the minimizer of f, then the first order condition is that the derivative of f with respect to f1 has to be 0 if it's a minimizer. And so the last term goes away. Okay, and the last property that we'll use is if f is the sum of two convex differentiable functionals. Then the Bregman divergence for F is the sum of the Bregman divergences for A and B. Okay. So these are the properties that we're going to use for the Bregman divergence. Okay. So, all right, so now the goal is to prove this second statement here, which is bounding the RKHS norm in terms of the infinity norm. And the notation that we're going to use here is, first of all, we have the empirical loss which is defined as always. And then the regularizer is going to be n. Yep. And then the Tikhonov functional is T sub s. Okay, so this is our notation. And first thing to notice is that if V is convex in F, then the empirical risk is also convex because it's the sum. And the other thing is that N is convex in F because the norm is convex. And both of these should be differentiable. These may or may not be extra assumptions that we're making here. But anyway, let's just say these are both. Okay, so this is the notation. And all right, so there's two steps to this. One of them is easy, the other one is hard. So, so the first step is going to be just decomposing, just writing this square norm of the distance between f sub s and f sub siz as the sum of two Bregman divergences. And then the second step is going to be to show that this sum satisfies the bound that we want. Okay. So the first one is pretty easy. And just comes from the fact that we had, this is literally just straight from the definition. So let's see. Oops. Yeah, okay, so this is just using, what did I write there? Yeah. This is just using that fact that we showed right here, which is n is a square norm. And so the Bregman divergence between u and v, or these two functions with respect to, so the Bregman divergence divided by n is equal to the norm of their difference squared. Okay, so that's what we just showed here. Okay. I should really write this. Okay, so the second step is where all of the calculation is going to be. I'm going to run out of space. Okay. So we'll start with lambda multiplied by this thing on the left-hand side. So something that we can say about this is because we have the Tikhonov functional being the sum of n and this empirical risk, this is non-negative. So the Tikhonov functional has to be an upper bound for the regularizer. So what we can say is that this was lambda times the regularizer. So that this is bounded by the sum of the Tikhonov functionals evaluated at the same functions. Okay, and I'm going to go ahead and start labeling these. So A is the right-hand side here. Now, since f sub s sup lambda minimizes the Tikhonov functional. And so by the, I guess, the second property, we can write the Tikhonov functional like this. The Bregman divergence with respect to Tikhonov. Okay, and we can do the same thing for the other term. Okay. So we can go ahead and plug these in to this right-hand side here. And what we have is that this statement is true. So we plug these two statements in for this and this, and what we get is this. Now, the important thing to note here is that these two pairs of functionals have the same regularizer, because the regularizer does not depend on the particular training set except via the function that you're plugging in. And the function is the same. And so the regularizer, like the end terms, all cancel. And this I'm going to call B. Let's see. Okay. Okay, so we canceled all of the regularization terms, and then we can do the same thing again and cancel almost all of the empirical risk terms. So these two and these two are identical except at the ith point. Because the functions are the same, but the training sets differ at the ith point. And so again, all of the terms except for the terms at the ith point are going to cancel. And so you get this. So we just have 4 terms left. And the last step is we notice that V we assume to be L Lipschitz. So we can bound the, let's see, which terms are we bounding? So we can bound these pairs of terms, these differences, can bound their magnitude in terms of the subnorm, which was our goal. If you look over at number 2, we're trying to get a bound in terms of the infinity norm, and we can get a bound on these differences in terms of infinity norm from the Lipschitz condition. I'm going to have to erase. So I'll call this D.
I have a quick question.
Yep.
On this side here, on the number 2, the second part.
Yep.
On this side here, where you go first, you have the divergence of n on there.
Yep.
Then you jump into the divergence of I of x, based on that I of s equals I of s plus n.
You mean T of x?
T. Is there a difference there from being like, so n should be the T of s minus I of x? Instead of like, does that even matter? You're replacing n by a sum of t. Like, are you canceling I? Like, what do you do?
Let's see here. So this is just the definition of T,
Right.
is that it's I sub s plus lambda times n.
Right.
And because I sub s is non-negative, you know that the value of this functional at a particular function has to upper bound the value of
Oh, okay.
this on the right.
Okay, that's why you have the inequality there. Okay.
Yeah. Yep. That, okay. All right. Okay. And so we're going to use the Lipschitz condition, and we say that that last statement is why is it over n? Oh, okay. Yeah, so there's a 1 over n in front, and then we have this Lipschitz constant L, and we have 2 differences that we're bounding, so it's 2 times L over n, and then it's the infinity norm. This is just from the definition of Lipschitz. Okay. And so if we reverse all this and go way back to statement 1, if you trace all the way back, then what we've just shown is that this is true. Okay. So that's really the hard part of the proof. And so then, now that we've shown that, we have these 2 statements are true, and then, like we said in the beginning, I erased it, but you get this statement follows from these 2, and then you get beta n. I'll just write it again. Okay. L squared kappa squared over lambda n. This is our beta n. This is the stability constant for Tikhonov regularization. Okay. So then the last thing to do, so now there's really one more step before we know that Tikhonov generalizes. And so there was, in addition to this stability criterion, there was one more condition, which was that the loss be bounded. And we didn't quite assume that the loss was bounded. We assumed that it was Lipschitz. And so that's the last step, is we're going to show that the assumptions that we've already made imply that the loss is bounded and gives a concrete form for that bound. Let's see here. Okay. So the things that we're assuming are that V is L Lipschitz, that the reproducing kernel is bounded, and there's one more assumption that we add, which is when you evaluate V for the zero function, then that is finite and bounded by this constant C0. And this seems like a reasonable assumption to me. Okay. Then you get two facts. So the first one is pretty quick. It's like 2 steps. So we'll get a bound on this regularization term, or forget that. So on the square norm of the minimizer of Tikhonov. So we know that because it's because this term is exactly the regularization term, Tikhonov is a sum of empirical risk plus regularization terms, so lambda times regularization terms. So this thing on the right has to bound this thing on the left. And then we know that Tikhonov evaluated at its minimizer has to be less than or equal to Tikhonov evaluated anywhere else, including at the zero function. And when you write that out explicitly, then because we assumed that the loss is bounded for the zero function by this C0, then the first term is bounded by C0, and then this square norm of the zero function is equal to 0. So we can bound lambda times the square norm of the minimizer of Tikhonov by C0. Okay, and then the second fact is the one that we want. Is a bound, uniform bound on the loss. So we'll use the triangle inequality to write this in terms of the loss at the zero function. Okay, so this is just the triangle inequality. Now wait, what did that? Oh yeah. This first term here, by the L Lipschitz condition, has to be less than or equal to L times the infinity norm of their difference, which is just the infinity norm of F. And then the second term, by assumption, is bounded above by C0. Okay. Did we already show that? Yeah, there it is. Okay, and then we can use that first fact there to bound the infinity norm in terms of the RKHS norm. And then we'll use the fact that we just showed here to go ahead and bound this RKHS norm. And then what you get is this. So this is uniform bound on the loss. And that was the last condition we needed to show that Tikhonov generalizes. And we can go ahead and plug all these into our statement for the defect bound then. So this is from last class. We showed that the defect bound what was it? It was beta n plus n, beta n plus m times the square root of 2 ln 2 over delta. Okay, so this was our general statement for the defect bound, and then plugging these in, we get this. Okay, so this is the full defect bound then for Tikhonov, and this holds with high probability. Okay, and again, because beta n is decreasing as 1 over n, that was the sufficient condition for generalization. One other thing to look at here is the effect of lambda. So lambda in general, as you increase your training set size, is going to be decreasing. And so if lambda were to be decreasing too quickly, then actually this defect bound would not be decreasing to 0. It's slowing down the convergence. Basically, if lambda is going to 0 faster than 1 over square root n, then it doesn't go, the defect bound is not going to 0. Okay. And the final thing to note here is if you look at what happens when lambda goes to infinity, then our bound, if Yeah, I think you're right. Yep. Okay, and then if we take lambda to infinity, then beta n is going to 0. So what that's saying is that if lambda goes to infinity, then your learned function isn't varying at all. Okay, so the loss isn't going to change if you change the training set. So you're ignoring all of your data if lambda is going to infinity. And yeah, okay. So those are the points to make. I think that's basically it for me. So Tikhonov does generalize under certain conditions on the loss and on the RKHS and on lambda. So, okay. Questions about this? Or? Yeah.
So what does it imply for the losses that don't satisfy the condition? What do we do?
So if they don't satisfy the conditions, then we can't make this conclusion. I don't know if there's a converse result. Is that if they don't satisfy the conditions, then Tikhonov doesn't generalize. I don't know if that has been shown. Yeah.